All right, you guys, how you doing? Day 7 of our current predicament. It's Friday, March 20th. The news is not great today. This will get worse before it gets better, so stay well, stay in, and please, again, follow all of the health advice and advisories that we've been given and continue to be updated on a daily basis. The next 4 lectures, we'll talk about vision, and I love this part of the course. I spent a lot of years of my life studying light-sensitive proteins, opsins, and trip channels, and light sensation in skin, and I so wish we could be in the lecture hall where I could expound on such things. But in any case, let's get started. And we'll start small with the molecular physiology, and then we'll move out, zoom out over the next few lectures. But let's start with the basics and signal transduction pathways that hopefully some of this should be a little bit familiar, and we'll layer in some depth on top of what you hopefully already know. So we'll start off with molecular physiology within the retina. Byrne-Levy is pretty good. Chapter 8 has some information for you on this, but I've layered in a lot of my own figures from my own papers, so you'll want to use the lecture slides as your primary resource. We'll remind ourselves of the basic anatomy, so we'll discuss the layers of the retina and the cellular structures and connections, that are present in each layer. 2 different types of ocular photoreceptors. Okay, so that's just complicated language for rods and cones. You've heard of rods and cones before. We'll revisit those. The major events that occur in the rod phototransduction pathway, but keep in mind that those are qualitatively similar to the events in the cone phototransduction pathway. It's just that rods are a little better studied. There are some quantitative differences, but qualitatively, rods and cones work the same way in terms of their light-activated phototransduction signaling pathways. Where and how the retinal chromophore is regenerated. Okay, so you've learned previously a little bit about opsins, rhodopsin and the cone opsins, and you know that they are, or you should recall, or you soon will recall, that they're G protein coupled receptors, but they're not light sensitive all by themselves. They need a binding partner, and that binding partner is retinol. Right? Retinol is a derivative of vitamin A, and it is the binding partner of opsins that results in the opsin being light sensitive. So it cycles between a cis and a trans conformation. If that sounds fuzzy, don't worry, we'll talk our way through that. But the retinal chromophore needs to be regenerated. Trans retinol needs to be converted back to cis retinol so that the opsin can retain its photosensitivity, or its photosensitivity can be reset, might be a better way to think about it. And then the circuitry of the retina. And if you want to write down 3 important cell types right now, or maybe a few more than that, but we'll talk about rods, we'll talk about cones, we'll talk about bipolar cells, and we'll talk about retinal ganglion cells. Those are the key cells that or the key cell types that we'll focus on. All right, so the basic anatomy of the eye, I won't spend too much time on. There's 3 layers, and if you need to revisit this, you can go to Copen and Stanton, Byrne-Levy, your textbook, chapter 8, and remind yourself about the anatomy. But the outermost coat is, or the outermost layer is a fibrous coat that includes the cornea. So I'm pointing at the cornea here. It's translucent. And the cornea is continuous with the white of your eye, which is the sclera. So the sclera is mainly epithelial tissue. It's protective, surrounds the eye. The middle layer is the vascular coat. So that's where you will find the iris. So the iris is here, which will determine the diameter of the pupil. So the iris is important. And the choroid layer. And the choroid layer is where you will find the vasculature, blood vessels that supply the eye. And the innermost layer, and the one that we'll spend the most time on, is the retina. So I'm circling the retina here. And the cells that I mentioned a couple of minutes ago, the rods, the cones, the bipolar cells, the retinal ganglion cells, are all found within the retina. Muscles we've talked about recently, right? So the extraocular muscles like the superior and inferior recti, the medial and the lateral recti, the obliques. We talked about that in recent history, so you can go back to earlier lectures for a review there. But there are muscles that are important here. The sphincter, dilator, and ciliary body, which together determine the diameter of the pupil and also the curvature of the lens. So I don't want you to worry about all of the anatomy that's shown on this slide. I would never give you this figure and ask you to label it, but the key point is if it's part of the pathway that light takes from entering the eye to hitting the retina, then you should know the structure. Okay, so the cornea, the anterior chamber, the lens, the vitreous humor or vitreous chamber, and the retina are all structures through which light passes. You should know them, okay, and be able to name them in order in terms of which light passes through first. The function of the eye, of course, is to detect and allow perception of electromagnetic waves. Anything below 400 nanometers, anything with a wavelength below 400 nanometers is ultraviolet. We can't see it. Anything above 750 is infrared. We can't see it without filters. We can detect between 400 and 750 nanometers of electromagnetic radiation. And there's brightness and wavelength. And if we were in lecture, I would ask you to tell me which of the ocular photoreceptors is responsible for brightness and which of the ocular photoreceptors was responsible for wavelength. And you would hopefully be able to remind me that brightness is rods, how much light, the presence or absence of light, dim light versus bright light, and the wavelengths or color vision is your cones. You might remember that you have 3 cones, red, green, and blue, but we'll get to that and talk about it in coming slides. Key takeaway, the path of light. Cornea, aqueous humor, lens, vitreous humor, and the retina. You will recall the concept of refraction. When light moves from one medium to another, it is refracted, it bends, and the two structures with the most refraction in this pathway are the lens and the cornea. One of those is adjustable and the other is not. The cornea is not adjustable. The lens can take on a more flattened shape or a more rounded shape depending on whether you're looking at something that's close up or if you're looking at something that's further away. So the refraction of light by the lens is adjustable. The refraction of light by the cornea is fixed, and the two of them together account for the majority of refraction along this pathway of light. And the fovea is the point of sharpest focus. So the fovea is the region of the retina onto which light is focused. And you've learned that in earlier physics courses, so I won't expound upon that physics here. We will discuss in detail the layers of the retina, and before you start trying to write down everything I'm going to say while we look through this slide, it's on the next slide for you, right? So this slide here has at least a paraphrased version of what I'll speak to on the previous slide. So most of the information is here. You might want to make some additional notes, but don't worry about trying to copy down absolutely everything. Okay, so we're looking at layers of the retina, and we're starting with, let's start down here at layer 1, which is the layer of the retina that's closest to the choroid. So this would be the outermost layer of the retina, and it's the pigment epithelium or retinal pigment epithelium. And the RPE cells are important because they contain melanin. This doesn't determine the color of your eye, right? That's determined by pigment that's present in the iris. However, the RPE contains pigment that's important for absorbing light, right? Melanin absorbs light, and that's important for high acuity vision. Light bounces, it refracts, it reflects. So if you were to have light hit the photoreceptors, which are here in layer 2, and then that light was to bounce around and reflect and refract and go and hit other photoreceptors, hopefully you can see how or imagine how the bouncing and reflecting and refracting of light would not facilitate high acuity, sharp vision. We want to activate these photoreceptors where the light is focused in the fovea, and then we want to absorb that light so it won't bounce and refract and reflect and go and activate photoreceptors elsewhere. So that's in the importance of the RPE. Number 1 is it contains pigment, specifically melanin. And number 2, as we'll see, or as you may recall from earlier courses, the outer segments, which I'm pointing at here, I'm pointing at the outer segments of the photoreceptors, they're constantly being replaced. So if they're constantly being replaced, then we need a mechanism to take up, to engulf, to phagocytose the ends, the tips of these outer segments and recycle them. So the RPE, retinal pigment epithelium, also has phagocytic capabilities, and it can take up, it can recycle, it can break down the ever extending tips of the outer segments of the photoreceptors. Okay, so layer 1 is important for absorbing light, preventing it from bouncing around, and also engulfing, phagocytosing the tips of the outer segments. Layer 2 is your photoreceptors, or at least the outer segments of your photoreceptors. So we can see rods that look like little rods and cones that look like little cones present in layer 2. The outer limiting membrane, layer 3, is the boundary between the cell body of the photoreceptors and the inner and outer segments. This would be the inner segment, this would be the outer segment of a photoreceptor. The outer nuclear layer, layer 4, contains the cell bodies of the photoreceptors. Layer 5, the outer plexiform layer, contains the synapses between the photoreceptors, shown in green, and other important cells, shown in purple, the bipolar cells. We'll spend a lot of time talking about those. Mueller cells, cell bodies, are found within the layer 6, inner nuclear layer, and horizontal cells and amacrine cells. Here's a horizontal cell. It's labeled in, or it's colored in orange, and the amacrine cell is also colored in orange. Horizontal cells and amacrine cells are essentially interneurons. We won't talk too much about amacrine cells. I'd like you to know that they're here in the layer 6, the internuclear layer. The horizontal cells we will talk about in a little more detail. Those are inhibitory, and they are important for lateral inhibition in this system, but we'll come back to that next lecture. Okay, so but you can put a circle around horizontal cells and amacrine cells. They're an important part of this pathway. Put a circle around rods and cones, and definitely put a circle around bipolar cells. We'll spend a lot of time talking about different types of bipolar cells. Okay, so all of these other cell types, the bipolar cells, the Mueller cells, the amacrine cells, the horizontal cells, are found in layer 6, the internuclear layer. Your inner plexiform layer, layer 7, also contains synapses And the most important synapses, or the ones that are most relevant to us, are synapses between the bipolar cells and the retinal ganglion cells. The retinal ganglion cells are the cells, or the neurons in this pathway that fire action potentials. Bipolar cells are neurons, but they don't fire action potentials. Their job is to release neurotransmitter when they're excited or when they're inhibited, in some cases, onto the retinal ganglion cells. And the retinal ganglion cells are the primary afferents in this pathway. You can find the retinal ganglion cells in layer 8, the ganglion cell layer. They have axons that converge in layer 9, in the nerve fiber layer, and these bundle into the optic nerve, which leaves the eye at the optic disc. And we'll talk about the pathway it takes to the thalamus and beyond in coming lectures. And then the last layer is the inner limiting membrane, and this would be the boundary between the retina and the body of the eye, containing the vitreous humor. So one key takeaway is here. The path of light. Light actually bypasses the cells, the retinal ganglion cells that it will ultimately excite, and it goes all the way to the back of the retina, where it first excites the photoreceptors, then the bipolar cells, and then the retinal ganglion cells. So the path of light is going in one direction, and the path of signaling is going in the other. And so for those of you that are maybe more engineering minded, maybe take some time and think about, could you design a better retina, and why is the retina organized the way it is? Why can't we have kind of an inverse organization where the bipolar cells are here, or sorry, the photoreceptors are here, the bipolar cells are in the middle, and the retinal ganglion cells are at the back? Take some time to think about the consequences of signaling if the organization in the retina was inverted, right? So people often talk about the backwards or inverted organization of the retina, but if you take a few minutes and think about it, you should be able to come up with some reasons why this evolved the way it did. Okay, but I'll let you maybe do that on your own time, and we can revisit it later. But take some time to think about that. So I won't read through this slide for you. It's a summary of everything that I talked through as we were looking at the previous slides. So these are kind of your Coles notes. So these are the basic key points about each of those 10 layers. But hopefully you made some additional notes as we were going through key points on the previous slide. Okay, so let's zoom in on photoreceptors, rods, and cones. 4 basic components. Whether we're talking about rods or cones, there are 4 main components. There's a cell body, so I'm circling the cell body for you on the slide. There's the inner, cell body would be here, right, where you have the nucleus and ER and all of the business stuff of the cell. And then you have the inner segment, and you have the outer segment, and then you have the synaptic terminals. And if you go back and look at the previous 2 slides, you will find those in layer 4, layer 2, and layer 5, respectively. The inner segment here is rich in endoplasmic reticulum, mitochondria. These photoreceptor cells are constantly making protein, specifically light-sensitive protein called opsins. It's synthesized in the inner segment, and then it's transported to the outer segment. The outer segment contains all of these flattened discs. So imagine an intracellular vesicle that you squish down so it looks like a pancake. So all of this stack of membranes here are all free-floating discs. Think of them as flattened, squished vesicles. And then all of that, of course, is intracellular. Those are intracellular, free-floating discs, flattened vesicles, all surrounded by plasma membrane, which is cut away here in this cartoon so that you can see the free-floating discs. all of which are packed with light-sensitive protein opsins. Okay, so the outer segment contains stacks of membrane discs, flattened vesicles that are rich in the photopigment. So photopigment, the light-sensitive protein, is opsin plus retinol. Right? Opsin itself is not light-sensitive. For it to be light-sensitive, we need opsin, rhodopsin in the case of rods, cone opsins in the case of cones, plus retinol. Okay? And these vesicles are constantly being made and packed with opsin and pushing out. So hopefully then it makes sense why we need something to engulf these tips of old worn out vesicles, old worn out opsins. And that's a function, if we were in lecture, I would ask you to remind me, that's a function of which cell layer, that's cell layer 1 of the retina, and which cells in that layer, the retinal pigment epithelium. All right. So rods versus cones. This is a figure from your textbook, and I've added in the wavelength sensitivity or absorbance spectra of the rods with a peak sensitivity at about 500. Okay, so rods are maximally activated. Rhodopsin is maximally activated by 500 nanometer wavelengths. The cone opsins differ from about 420 to 530 to 560 for the short, medium, and long wavelength sensitive opsins. So let's just back up. Your textbook correctly refers to a blue cone, a green cone, and a red cone. So rods only express one type of opsin. They all express rhodopsin. Because there are no other types of rods that express opsins with a different wavelength sensitivity, all rods can give you information on is how much light, the intensity of the light. Rods can't differentiate between different wavelengths of light because they all express the same opsin, which is rhodopsin, and maximally sensitive at 500 nanometers. Okay, so rods are how much light, but they don't give you information on the wavelength of light. Cones will express one of 3 different types of cone opsins. So your book correctly refers to, your textbook correctly refers to blue cones, green cones, and red cones. Blue cones express the opsin that you would correctly call short wavelength sensitive opsin that is maximally sensitive at about 420 nanometers, and that's in the blue range or violet blue range. Green cones express medium wavelength sensitive opsin, which is maximally sensitive around 530 nanometers, which is within the green range of the electromagnetic spectrum. And then red cones express long wavelength sensitive opsin, which is maximally activated at 560, which is actually not quite in the red territory, which would be around and above 600 over here. However, it's the only one that's going to be appreciatively activated by red wavelengths. So even though it's in yellow territory, if you look at the electromagnetic spectrum, these are correctly referred to as red cones because they'll be activated in response to, they will be the opsin and the cone that is activated, maximally activated in response to red. Okay, so short wavelength, medium wavelength, and long wavelength sensitive opsin expressed respectively in blue cones, green cones, and red cones. Rods only express rhodopsin, and they're only giving you information on how much light, but not the different wavelengths of light. Okay? Different wavelengths of light, i.e. color vision, are your cones. Okay, so on this diagram, we're just looking at the abundance of rods and cones along different regions of the retina as we move away from the fovea or towards the fovea, which is the point of focus. Right? So the fovea is the region of the retina where light is focused. The region of the retina where light is focused is responsible for sharp, high acuity color vision. At the fovea, you would expect to see, hopefully you would expect to see, if we were in lecture, I would ask you what you expect to see. Do you expect to find rods or cones at the fovea, if that's your point of sharpest high acuity vision? And hopefully you would tell me that's where you would expect to find cones. And that's exactly what you see. If you look at the density, receptor density is our y-axis here, and we have a huge density of cones at the fovea. And then as we move away in terms of degrees, 5 degrees, 10 degrees, 20 degrees, 60 degrees away from the fovea in either direction, we see a decrease in the number of cones and an increase in the number of rods. Okay, so foveal regions are responsible for high acuity color vision, and extrafoveal regions outside of the fovea are important for intensity, light intensity, how many photons versus the quality of those photons, which is a function of the cones. At the optic disc, that's where the axons of the retinal ganglion cells converge and leave the retina, leave the eye at the optic disc. That's a really busy, high traffic area. All of those axons are converging and leaving the eye. There's no room for photoreceptors. So there are no photoreceptors. So you can see the receptor density at the optic disc is 0 for both rods and cones at the optic disc. So that's referred to as an anatomical blind spot. However, you don't perceive a blind spot because that's taken care of by visual processing at higher levels. So in the visual cortex, the striate cortex, V1, that blind spot is eliminated, we'll say. So you don't perceive a blind spot, even though there absolutely is an anatomical blind spot at the optic disc. So the fovea is the focal point. The macula or the macula lutea is the super focused point. So you can think of the macula as being the central point of the fovea. So the fovea is the general point of highest focus, and the macula is the specific region in the fovea where the focus is absolutely highest. Okay, so key points: cones in the fovea, rods in extrafoveal regions. All right, so here we're looking at an opsin. By far, the best studied G protein coupled receptor, GPCR, is rhodopsin. It's kind of the benchmark for all other GPCR studies. So as you would expect, hopefully by this point, you know the general structure of a GPCR. So you have 7 transmembrane spanning helices, an extracellular N-terminus, if you remember a little bit of protein biochemistry, and an intracellular C-terminus, and an intracellular G protein binding site. The opsin itself, this is rhodopsin, is not photosensitive. In order to be photosensitive, we need the binding partner, the chromophore. Chromophore is something that absorbs light. Okay? So 11-cis retinol is the endogenous derivative of vitamin A that allows the opsin to be photosensitive. So it's bound, and there's a binding pocket here between helices 6 and 7, where the 11-cis retinol fits and binds. And the first step in signal transduction in this pathway is photoisomerization. So 11-cis retinol will absorb a photon of light, which will convert it or photoisomerize it from 11-cis to all-trans retinol. And without going into too much chemistry here, hopefully you can appreciate that this structure is kinked, it's bent, and this structure, the all-trans structure, is it's straightened out. And so if we were in lecture, I would kind of I would lift my arm and bend it at the elbow, and then I would straighten my arm out. And I'd ask you to think about as I straighten my arm, as I extend at my elbow, I'm pushing out. If I'm 11 cis retinol and I'm photoisomerizing to all trans, I'm pushing on helix 6 and helix 7. And I'd ask you to imagine how that might produce a conformational change. And that's exactly what it does. As we photoisomerize from 11 cis to all trans, the helices take on a new arrangement. And those changes are particularly profound at this intracellular C terminus of the GPCR, and specifically, it will open up the G protein binding site. Okay, so key takeaways: when 11 cis absorbs a photon of light, photoisomerizes to all trans, that causes a conformational change in the opsin, particularly at the C terminus, that opens up the G protein binding site. Remember, anytime you open up the G protein binding site, now the G protein can bind, activate, and go off and do its thing on its specific targets, whatever those targets are. All right, so phototransduction is summarized on this slide. HV, of course, is a proton. So proton binding will photoisomerize cis to trans retinol, which will activate rhodopsin. And I'd ask you, if we were in lecture, to remind me what the G protein in this pathway is. And some of you might recall transducin. So rhodopsin will activate transducin. And the target of the alpha subunit of transducin is phosphodiesterase. So I haven't spelled that out for you on the slide, but hopefully you recall phosphodiesterase. And the function of phosphodiesterase is to cleave cyclic GMP into GMP. As levels of cyclic GMP fall, CNG channels, which we saw previously in the olfactory system, CNG channels will close. And remember, CNG channels are non-selective. They're permeable to sodium and calcium. So if CNG channels close and you lose the inward directed depolarizing current, that's going to lead to hyperpolarization. Okay, so in the presence of light, photoreceptors hyperpolarize. And that might seem a little backwards, but we'll unpack that a little in coming lectures. Always true. This is always true, and write it down now. In the presence of light, photoreceptors hyperpolarize. Okay? And in both rods and cones, when they hyperpolarize, that will reduce glutamate release. Okay? That should make sense, right? When we depolarize, voltage-gated calcium channels open, we exocytose neurotransmitter. Okay? But in these cells, that's happening in the dark. In the light, photoreceptors will hyperpolarize, and that will reduce neurotransmitter release, specifically glutamate release, that is normally happening in the dark. Okay, so key takeaway: photoreceptors are depolarized in the dark, and they hyperpolarize in the light. Okay, let's work through the figure that's shown in panel B at the center of the slide. In the presence of light, RH is rhodopsin. Photoisomerization from cis to trans retinol activates the rhodopsin, in turn activates transducin, in turn activates phosphodiesterase. That will cleave cyclic GMP into GMP, leading to closure of CNG channels, okay? Closure of CNG channels, and hyperpolarization of the membrane. And that's not imminently clear the way this slide is presented, right? The plus sign here means rhodopsin activates transducin. Positive sign here means transducin activates phosphodiesterase. Once we have phosphodiesterase, we cleave cyclic GMP into GMP, and just make a note that that results in the closure of CNG channels that would otherwise lead to depolarization. So in response to light, the photoreceptor is going to hyperpolarize, not depolarize. It's depolarized in the dark and it's hyperpolarized in the light. The panel down at the bottom just shows that this is an extremely complex pathway with a number of different interconversions and a number of different modulators. The two that I'd like you to know, I've written in red at the bottom, rhodopsin kinase and arrestin. So anytime we turn a signal on, we also need to be able to turn a signal off. So once we activate this pathway in response to light, how do we turn it off? And off is rhodopsin kinase. And rhodopsin kinase is a kinase, a protein that will phosphorylate rhodopsin. And once rhodopsin is phosphorylated, arrestin combined. And once you have rhodopsin that's phosphorylated and arrestin has bound, that rhodopsin is turned off. And once rhodopsin is turned off, it needs to be reset. So it needs to unbind from arrestin, it needs to be dephosphorylated, and it needs to be given back a fresh chromophore of 11-cis retinol. So we need to take away the all-trans retinol, and we need to give back an 11-cis retinol, and then we are reset, and we're ready to go again. And that takes time, right? So you've probably walked into the light from a dark room, or you've walked into the dark from a light room, and you know that it takes a few minutes to adjust. And that's because all of the complex interconversions and steps that are shown on in this lower panel here that you don't need to worry about at all take time. Okay, but I'd like you to know that rhodopsin kinase and arrestin are involved in turning this signal off once it's initiated.